Hello guys, today we are going to look into activation function that are part of deep learning. But before that, I have a question for you. Have you ever wondered how artificial intelligence make decisions? Please share your answer or what do you think in the comment box below. I want to cover some basic concept before we jump into activation function. Let's start with the foundational relationship between AI, machine learning and deep learning. We can describe artificial intelligence AI to build machines or systems that can mimic human intelligence. In simple terms, we can simulate human behavior to perform tasks that require human intelligence, such as problem solving, ability to active learn, and decision making. Now let's move to our next part, machine learning, ML. We can describe it as a methods for learning from data or past experience which automates the building of analytical model. In simple term, we can say machine learning uses techniques that enable a machine or system to learn from data without being explicit programmed. So instead of following pre-written rules, ML models learn patterns from data to make prediction or decisions. For example, we can create a spam filter by showing ML model thousands of examples. This process automates the building of an analytical model. I hope this part is clear now. Let's move to our next part, that is deep learning. This involves computation through multi-layer neural network and processing. That's the core of deep learning. In simple terms, we can say deep learning models are inspired by the structure of human brain. They use multi-layer neural network to process data. This network composed of interconnected neurons. This neuron can learn, process vast amount of complex data such as image, sound, text with high degree of accuracy. This enables deep learning to handle tasks that are too complex for traditional machine learning. For example, image recognition or natural language. I hope till here you have understood everything. Let's repeat one more time. Artificial intelligence describe the simulation of human behavior and intelligence. Machine learning provides technique or method to learn from data based on the pattern. Deep learning models are inspired by the structure of human brain and use multi-layer neural network to process the data. So, deep learning is a subset of machine learning. Machine learning is a subset of artificial intelligence. Now we'll look into, here is the animation version of neural network, how it works, but we'll not go into more detail because I'll create a separate video on this and I'll put the link of that video in the description below. So if you're interested, please go and check it out. Moreover, in this video, I'll focus on single neuron, also called as perceptron. So here is a few key component of a neuron. First is the input. The input could be anything like pixel value of an image or a data from a spreadsheet, because these are feature we feed to the neuron. So we can represent the input as A1, A2 and so on up to n number of inputs. Second part is weight. Each input is associated with corresponding weight. So suppose if we have an input A1, then it will have a corresponding weight W1. Similarly, input A2 will have weight W2 and so on. Therefore, weight represent the importance or the strength of corresponding input. A higher weight means its input has more importance. Moreover, when we start the training, the weight value are randomly assigned at the initial stage. The system then learns the base weight automatically during training. So, when we apply the training algorithm like backpropagation or gradient descent, the weight will automatically gets updated. Therefore, we can say during training, these weights are adjusted to reduce the difference between actual and expected output so that the model can learn, and additionally, the weights of the networks are at their optimal level to make accurate predictions. Coming to our third key component, that is bias. We can think bias as a special number that stays the same. It helps us shift the entire function either left or right, giving the model more flexibility to learn. So the bias is a special input that always has the same value. And the bias also has its own weight, which is learned during the training period, just like other weights in the network. The bias weight start with a random number and get adjusted by training algorithm like backpropagation or gradient descent. That's all about bias. The fourth key component is summation. This refers to the calculation of weighted sum of input addition to the bias value. Now, suppose we have inputs A1 and A2 with weights W1 and W2, and we have some bias. For example, let's say the bias value is 1. We can express this mathematically. Here we have each input multiplied by its corresponding weight, and we then sum them all up, and so on for all n number of inputs. Finally, we also add the bias. In vector annotation, this would be a dot product of weight and input plus bias. Now, the result of this summation is passed to the activation function. So, that result is passed to the fifth and the final component, that is activation function, which is our main topic for today. So now let's try to understand what an activation function actually means. An activation function is a very important feature of a neural network because activation function make neural network capable of learning complex things by helping neurons to decide when to activate and when not to. There are generally two types of activation function. First one is linear or identity activation function. Second is nonlinear activation function. Let's see the difference between linear and nonlinear relationship with a simple example. First, in the linear dataset, as our x value goes up by a constant value, that is by 1, and y value also goes up by a constant value by 2, this constant and predicted change is a key sign of linear relationship. Now, let's look at two examples of nonlinear data. In first table, our x value goes up by a constant of 1 but the y value increased by a difference value each time. First by 1, then by 3, then by 5. In second table, our x value goes up by a constant value, that is 2, but our y value change by 2, then by 6, then by 10. The main point over here is that the change in y value is not fixed or constant, that is non-linearity. If we draw the relationship, then in the graph our linear data will show a perfect straight line, but when we draw the graph based on our non-linear data set, we get a curved line. This line bends, twists because of rate of change between the data point which are not constant. Moreover, in the real world, most data follows complex patterns. That's why if we want our model to understand pattern like cosine, logarithmic, exponential, cubic, or quadratic relationship, we need to use activation function. Additionally, if we only use a simple linear function in our network, we would run into two big problems. First one is backpropagation would be impossible. A linear function slope is a constant number. This means it doesn't change with input value. Therefore, when a neural network weights are updated by training algorithm like backpropagation to minimize its mistake by comparing actual and expected value, so with a constant slope, it's impossible to make those important changes. Second problem is all layer would become one. No matter how many layers you add to the neural network, if every layer uses a linear activation function, the final result will still be a simple straight line combination of the first layer. So basically, we are creating a stack of single layer network which can only learn very simple relationship. This is where activation function comes in. They add non-linearity to the network. This allows the model to learn and understand complex curved relationship we see in real world data. Without them, our neural network could only find straight line patterns. I hope now you understand why we need the activation function. Let's look at some of the most common activation function we'll be covering over here. The first one is sigmoid, second ReLU, third tanh, fourth softmax. So we'll start with the sigmoid now. Meet the sigmoid function. The mathematical formula is 1 divided by 1 plus e to the negative x. Don't worry about memorizing that. Just know what it does. Sigmoid take any number from negative infinity to positive infinity and transform it into range between 0 and 1. It creates this beautiful ash shaped curve. Back in the day, this was perfect. You can interpret the output as probability. Getting 0.8, that means I am 80% confidence on something. Getting 0.2, I am 20% confident on something. But sigmoid has two major problems. First, the vanishing gradient problem. When your input gets really large or really small, the slope become almost flat. That means almost no learning happens. Your network get stuck. Second problem, sigmoid output are never negative. This create weird training dynamics that slows everything down. Today, sigmoid is not used anymore in hidden layers. You will only see it in binary classification outputs like cat and dog problems, although it has a huge legacy, but now largely replaced by the ReLU families in hidden layers. That's all about sigmoid. Now we'll look into the second part of activation function, that is tanh, hyperbolic tangent. The formula is e to the x minus e to the negative x all divided by e to the x plus e to the negative x. Tan h fixes one of the sigmoid problems. Instead of 0 to 1 output, it outputs from -1 to +1. That means it's centered around 0, and that actually helps networks learn faster. But tan h still has that vanishing gradient problem. For really large positive or negative inputs, the gradient becomes tiny and the learning slows to a crawl. These days, you might still see tan h in some recurrent neural networks, especially in older natural language processing models. But for most deep learning application, it has been replaced by something much better. Yes, ReLU. And that's our next part. ReLU as rectified linear unit, simple and powerful, and better than activation functions like hyperbolic tangent and sigmoid for hidden layers. The mathematical formula is just max of 0 and x. That's it. It means if the input is negative, then output 0. If the input is positive, then output the exact same number. Therefore, when we see the graph of ReLU, we observe the flat line at 0 for all the negative inputs, whereas for the positive inputs is linear. This is the simplicity of ReLU. It also solves the two major problems that we have seen with the activation functions like sigmoid and tan h. With its three features: first, the system needs to compare a number to 0, no complex math, therefore it performs tasks at lightning speed. Second, it completely solves the vanishing gradient problem, at least for positive numbers. The gradient is either 0 or 1, clean and simple. Third, it creates sparsity. Lot of neuron output exactly 0, making the network more efficient. Moreover, ReLU has one issue called dying ReLU problem. Some neurons can get stuck and always outputs 0. Once a neuron outputs 0, its gradient is also 0, meaning it will never recover during training phase. This can be caused by poor initialization or high learning rates. Now just imagine a neuron having a bad luck with the weight initialization or having a too high learning rate and only see negative inputs. So negative inputs means ReLU output will be 0, correct? 0 output means 0 gradient. 0 gradient means no weights updated. No update means it will always see negative inputs. The neuron is permanently dead over here. In extreme case, you might find that 40% or more of your neurons are dead. That is like having almost half of your network doing nothing. Around 2010, when ReLU really became popular, suddenly we could train the neural network with dozens or even hundreds of layers. And to encounter the challenges of ReLU, we have leaky ReLU and parametric ReLU. Now let's see leaky ReLU. Instead of completely killing negative inputs, it gives them a tiny slope, usually 0.01. So if your input is positive, the output will be the same number as in ReLU. But if it is negative, instead of 0, you will get some small negative number. That tiny slope means that gradient is never completely 0. This simple change means neuro can now recover from being almost dead. They are never completely dead, so they can always start learning again. The trade-off is slightly more complex than ReLU, but is still incredibly fast, and you need to choose that slope value, though 0.01 works great most of the time. Since 2015, leaky ReLU is super popular, especially in generative adversarial network and computer vision model. Parametric ReLU takes the leaky ReLU one step further. Instead of you choosing the slope for negative values, parametric ReLUs let the network learn it during the training. Each neuron can even learn its own unique slope. Therefore, the neural network learns the optimal negative slope for each neuron. Different neurons can have different learned slopes, which leads to high performance vision models. Trade-off. The downside, you are adding more parameter to learn, which means slightly more computation. But for high performance application, it's often worth it. Now let's talk about softmax, the activation function you will use for multi-class classification. The mathematical formula is, but what it does is beautiful. Softmax takes a bunch of number, could be anything, and convert them into probabilities that sum to exactly 1. So if your network outputs 2.3, 1.1, 4.5 for cat, dog, bird, softmax might convert that to 0.2, 0.1, 0.7. Now you can say I am 70% confident that this is a bird. The cool thing about softmax is that it emphasizes the winner. The highest input get boosted even in the probability space. Softmax has been around since 1980 and is still the best standard for multi-class classification. Some things are just perfect the way they are, isn't it? Alright, decision time. Here's my practical guide. For hidden layer, start with ReLU and you can choose any of the ReLU family based on your use case. For output layer, it's simple. Binary classification like spam or not spam. Use sigmoid. Multi-class classification like cat, dog, bird, fish. Use softmax. Regression like prediction of house prices over time. Use no activation function, just linear output. And here is the historical timeline of activation functions. That's all about activation functions. Now go forth and build some amazing neural networks. Thanks for watching and I will see you in the next video. Thank you.